Have you ever wondered how AI tackles those classic brain-bending puzzles that seem, well, almost impossible for computers to solve efficiently? Today, we're diving into some incredible new research that does something different. It doesn't just teach an AI to find a single answer, it teaches it the very process of searching for an even better one. Let's get into how they pulled this off.
So, the puzzle at the heart of all this is the famous Traveling Salesperson Problem, or TSP for short. Imagine you're planning the ultimate road trip, or you're a delivery driver with a ton of stops. You've got this list of cities you have to visit, and your goal is to find the absolute shortest route that hits every single one before you come home. Sounds simple enough, right? But here's the catch. As you add more and more cities, the number of possible routes just explodes exponentially, making it unbelievably difficult to find the perfect one.
Okay, so how have we tried to solve this with AI in the past? Well, traditionally, most models are trained to be constructive. They look at the whole map of cities and just generate one single highly optimized route. That's it, their best shot. But the researchers behind this paper asked a really brilliant question: what if that first guess isn't the final answer? So they developed a whole new approach where the AI learns to take any given solution and methodically improve it, step by step, constantly searching for a better, more efficient path.
And this gets us to the core issue these researchers really wanted to solve. The salesperson's big problem isn't just about finding a route. It's about finding the absolute best route you can, given a certain amount of time.
This is the question that changes everything. If an AI gives you a pretty good delivery route, that's fine. But in the real world of logistics, even a tiny 1% improvement can save a company millions of dollars. So you can't just stop at that first guess. You need a way to keep chiseling away at it, to keep refining it. And this right here highlights what the paper calls a structural mismatch. Think about it. We train our AI models to produce a single one-shot solution. But then, in practice, we deploy them with a time budget. Like, hey, find the best answer you can in 5 minutes. The way we train them and the way we actually use them are totally misaligned. This research is all about fixing that.
So, how did they do it? Let's go inside their method. They call it NICO-TSP, which stands for Neural Improvement for Combinatorial Optimization. The whole system is built around this idea of teaching an AI the art of the search.
Now, I know this slide looks a little complex, but the main idea here is a really clever shift in perspective. On the left, you've got the traditional way of thinking about this problem. You focus on the cities, or the nodes. But NICO-TSP does something totally different. Over here in the edge-centric representation, it focuses on the roads connecting the cities, what the paper calls tour edge tokens. So instead of the AI asking, which city do I visit next, it asks a much more powerful question. Which two roads in my current route should I swap to make the whole trip shorter? This little change perfectly aligns the AI's view of the problem with the actual search process, and it turns out that's a huge key to its success.
The entire framework is really built on 3 big ideas. We just talked about the edge-centric view, focusing on the connections. Second, it avoids what are called positional encodings. Basically, it doesn't give each city a permanent number in the route, like you're the 5th stop or you're the 10th stop. By not doing that, the model becomes way more flexible and can handle routes with any number of cities. And third, it uses a super smart 2-stage learning process to train the AI.
Let's break that training down. First, in stage 1, it uses imitation learning. This is kind of like a student learning chess by copying a grandmaster's moves. The AI learns from a perfect oracle that knows the absolute best 2-step sequence of road swaps. Then, in stage 2, it moves on to reinforcement learning. Now, the student is playing games against themselves, discovering creative long-term strategies that maybe even the teacher hadn't thought of.
And this slide just illustrates that 2-stage process perfectly. In stage 1, on the left, you can see the oracle-guided imitation learning. The AI is basically being taught the basic textbook moves by a teacher who knows the best short-term swaps. Then it graduates to stage 2 on the right, group-based reinforcement learning. And here, it's not just copying anymore. You can see all those little AI agents running multiple search attempts in parallel on the same problem. It then learns by rewarding the strategies that find the best solution the fastest. It's this powerful combo of guided learning followed by creative self-discovery.
Okay, so the theory is super elegant, but does it actually work? Let's get to the results and see how this new approach really stacks up against the competition. The results are, and I'm not exaggerating, absolutely stunning. This table shows how different methods performed on a really tough 500-city problem. Remember, A lower cost means a shorter, better route. Look at the other methods. They're getting costs in the hundreds. NICO-TSP gets a cost of just over 17, which is incredibly close to the known perfect solution. And then look at the time. It finds this near-perfect solution in just 77 seconds. That's like 10 times faster than its competitors. Just incredible.
And here's a crucial point, something the paper calls scale robustness. Get this. NICO-TSP was only trained on problems with up to 100 cities. So when they threw a 500-city problem at it, something 5 times larger than anything it had ever seen before, it didn't just fall apart. While other models really struggled, NICO performed beautifully, proving that its underlying strategy is truly flexible and not just memorizing.
This also highlights what's called anytime performance. It's not just about the final answer. It's about how quickly you get a good one. The research shows that NICO closes the gap to that perfect solution incredibly fast. In some of the tests, it gets within just a couple percentage points of the best possible answer almost immediately, while other methods are still way behind. That speed is so critical when you're on a tight deadline.
And here's another key advantage. It's flexibility. NICO can start from a totally random route and find a great solution all on its own. Or, and this is super cool, you can give it a high-quality solution that was generated by another AI, and it will act as a refinement tool, basically polishing that already good answer to make it even better. It's a powerful addition to the AI toolkit.
Now, of course, no research is ever perfect, and a critical part of understanding science is acknowledging the limitations. The authors are actually very clear about what the next frontiers are for this kind of work.
There are really 2 main challenges ahead. First is massive scale. While it's fantastic at 500 cities, when you get up into the thousands, the sheer number of possible road swaps just explodes and performance does start to degrade. The second challenge is creating smarter teachers. The teacher it learns from in stage 1 is, by design, pretty short-sighted. It knows the absolute best 2-step sequence of moves, but it doesn't necessarily know the best 20-step strategy. Developing more far-sighted teaching methods is a huge area for future research.
So, what's the big picture here? What does all of this mean for the future of how AI solves these incredibly complex optimization problems?
I just love this quote from the paper because it perfectly sums up the takeaway. The goal here isn't to replace those old constructive AIs, it's to add a powerful new tool to the toolbox. You can use one AI to get a great first guess, and then use an AI like NICO to search for an even better one. They can work together.
And that really is the heart of it, isn't it? The real paradigm shift they're proposing here is moving away from just generating a single solution and moving toward learning the actual process of search itself. It's a fundamentally different and potentially much more powerful way for AI to approach problem solving.
This leaves us with a final and pretty fascinating question. The traveling salesperson problem is just one example of a hard optimization puzzle. What other massive challenges could we solve by teaching an AI not just to answer, but to search? Imagine applying this to designing new drug molecules, to optimizing global supply chains, or even creating more efficient computer chips. The possibilities are truly exciting to think about.